In the previous lesson, we spent a lot of time talking about sequences, and now we're going to get into series, and that's when we add them together. Now, we did address some series in the last lesson, but we're going to get much deeper into it, and specifically in this lesson, of course, with geometric series. And geometric series, just in case you need a reminder, this is when each term is multiplied. Use the title to create a definition, by a constant. We're going to call it R. It stands for common ratio, to get the next term. Now, technically, what I just told you was geometric sequence. Geometric series is when we add them together like we're going to do here. Now, just to slide the paper up for a moment and come into these little boxes of importantness. The explicit form of a geometric series is, slide the paper back down, we weren't done. Okay, now, the explicit form of a geometric series is, well, glad you asked. Okay, I could start, whoops, not A. No. These things usually use N to count by. So N is going to start at 1 and go all the way to infinity if it's going to be an infinite series. And we're going to use the explicit form of the nth term, okay? So A sub 1 and then R to the n minus 1. And if you're like, wow, that does not look a bit familiar at all, don't panic. Do not panic whatsoever. So here's what's about to happen. Let's slide up for just a second. By the way, there's another one coming. Just hold your horses. We're going to write the explicit formula for this. So let's just write the formula that gives us the next term. Not the next term so much as it is any term we want, the explicit formula. The next term would be recursive, and we don't want that. So that would take forever. So the explicit formula is going to be, well, let's see, I know the first term, and to go from here to here, I would multiply by what? Not obvious necessarily, but you can tinker with it a little bit. Best way to do it actually is do 1.6 divided by 0.32, and I'll go ahead and tell you we're multiplying by 5 here. Let me grab a calculator. I want to prove it to you. If we do 1.6 divided by 0.32, we get 5, but it needs to consistently work. So 8 divided by 1.6 is also 5, and 40 divided by 8 is 5. That one's a lot more obvious. So we're multiplying by 5 every time. But how many times would I multiply by 5? We'll see. If I wanted the first term, I would multiply by 5 none at all. If I wanted the second term, I'd multiply by 5 only once. If I wanted the third term, I'd multiply by 5 once, twice. So I always want one less than the term number. And the explicit formula for a series is where I'm adding a bunch of stuff together. So here's that summation notation again. You just saw it down here. But basically, I'm going to say, well, you know what? Let's start at 1. And let's add these forever. Now, I'm going to treat this like an infinite series because they said it was, okay? So does this infinite sum converge or diverge? And if it converges, find the infinite sum. So if I added 0.32 plus 1.6 plus 8 plus 40 times 5, which is 200, plus 200 times 5, which is 1,000, and then times 5, which is 5,000, and then 25,000. This gets really big really fast, and the numbers get much, much larger. So this one is going to diverge because the numbers get bigger. Okay, now let's turn this thing around. It's going to start at 40 and work backwards. So to turn a 40 into an 8, what would I do? Divide by 5. To turn an 8 into a 1.6, what would I do? Divide by 5. And same thing. So I would multiply by 5 to go this way. I would divide by 5 to go backwards, which is what this one is. So you could say I'm multiplying by 1/5. So the explicit formula is from 1 to infinity of 40. I don't know why I was going to put it in parentheses. No need. Let's not waste the ink on that. Let's waste the white out instead. 40, and then 1/5 to the n minus 1. So does this infinite sum converge or diverge? If it converges, find the infinite sum. So let's find out. I'm going to just add some stuff. So 40 plus 8 plus 1.6 plus 0.32 plus, okay, I don't know what the next one is, but it's 0.32 divided by 5 plus the one after that, which is 0.32 divided by 5 twice, that'd be 25, plus 0.32 divided by 5 times 5 times 5, that's 125, plus 0.32 divided by 5 to the 4th power, that's 625, plus 0.32, you're getting the hang of this, right? Times, divided by 5 to the 5th power, we'll go one more, plus 0.32 divided by 5 to the 6th power. I'm going to press enter, and we're going to look at this very logically and say, oh, I get it. Oh, I get it. Okay, so logically, what's the answer? 50. Does the infinite sum converge or diverge? Well, it converges. And if it converges, find the infinite sum. So the sum is, I'm going to write it the way it needs to be written. This sum is 50. That's it. Okay, now, geometric series could start with the first term, as we have done so far, or you could get a little technical and you could say they start with the 0th term. And if you want to do that, then we have a different explicit form, and it's a little bit simpler. So if you're like, oh no, another formula? No, don't panic. So we could start with the 0th term, go to infinity, and we would have a sub 0 of r to the n. Okay, it's a little bit easier to look at. This is the first term. We could start counting at 0. Don't get caught up in all the nomenclature and the counting and all that. Don't panic about that. But trust me, it works. Okay, so what makes a geometric series converge or diverge? Well, notice that this one got larger, so it tended towards infinity. This one got smaller, so it tended towards an actual answer. And here's the deal. When your common ratio is greater than or equal to 1, or if it's actually less than or equal to -1, I want you to realize what this truly means in a algebraic sense. If I say absolute value of r is greater than or equal to 1, I'm saying that r is greater than or equal to 1, or I could be saying that r is less than or equal to -1. It's the same situation. If you graph this on a number line right here, you would be dealing with the numbers less than or equal to -1, greater than or equal to +1. So this is equivalent to that. It's that they're all the same thing. And if you want a formula for what a series will converge to, well, good luck with that on most series, but geometric, we have a formula, and this is it. And it depends on where you want to start, a sub 1 or a sub 0, but basically the first term divided by 1 minus r. But this only works when r is between -1 and 1. This is going to be a very important concept later. We're going to need to know this, but let's just think about it logically. It makes sense. It really does make sense. When I multiplied by 1/5, the numbers got smaller. If we add them, we're able to add them and get a number that was, and here it is, 50 in this case. Because you look at it and you're like, man, that's 50. But yeah, you just keep multiplying by 5, the numbers tend towards infinity because you're multiplying by a number larger than 1, so the numbers get bigger and bigger. If r equaled 1, if you had a series where r equaled 1, then you would have a series where you'd say, all right, 4, for example. 4 is my first term. And then my next term is 4 times 1, and then 4 times 1, and then 4 times 1, and then, yeah. And you do this forever, you get infinity, right? That's why those also diverge.